Okay, very good morning, class. We'll now start our session on case-based reasoning. In the last class, we have discussed about locally weighted regression and radial basis functions. In locally weighted regression, we try to weigh the attributes locally and regress it with respect to the independent variables. Okay, so all the attributes are fit across a particular line by using only local weights. Means weights of the nearest neighbors are used in order to predict value of the dependent variable, that is the outcome variable. Okay, so we have used the local weights of nearest neighbors, that is why we call it as locally weighted regression. The name regression is because you are trying to predict some numerical value. If it is trying to classify, if the machine learning model is trying to classify something, then it is called as locally weighted classification. Okay, in that case, we take the weights of the nearest neighbors and try to predict the class to which the new instance belongs to. And in this instance-based learning, in the beginning class, we have covered k nearest neighbor. In the later class, we covered on locally weighted regression and radial basis function. But in radial basis function, though it is using the same distance metric as in k nearest neighbor, like Euclidean distance, it is using kernel functions. Kernel function is a function based on the distance between the new instance and the existing instance. Now, many kernel functions are constructed based on the k nearest neighbors considered, and the radial basis function is built in order to predict the outcome variable. Okay, so you understood the k nearest neighbor classification, right? If you are given if the machine learning model is trained, if the machine learning model is given some training examples, it will store all the training examples and it will not start any further processing until it is given a new instance. Now, in a n-dimensional plane, if you have lots of points like this, now a new instance is given, say star is given, which has to be classified. Now this star's features, means attributes, are compared with the features of existing instances. Say this new instance has attributes x1 and y1. Now the existing instance also has attributes say x2 and y2. Now the distance between this new instance and the existing instance is calculated by using the formula for Euclidean distance, that is x1 minus x2 whole square plus y1 minus y2 whole square. If there are more number of attributes, accordingly the formula will be changed. Okay, the formula will be tuned according to the number of attributes for a particular instance. Right? For simplicity, we are considering here only two attributes, x1, y1 and x2, y2. And if you want to measure the distance between the points, you can take it as x1 minus x2 whole square plus y1 minus y2 whole square. Right? Now, such distance is calculated between this new instance and the existing instances. Now, among them, whichever distance is lesser, you find the majority odd. Among all this, so say it is having lesser distance with only star instances. In that case, and little higher distance with circle instances. In that case, how many number of stars are near to this star, new instance star? 3. In that, based on that majority odd, it will be assigned to the star class. Right? Again, it depends on the k that is selected. This k is called as hyperparameter or metaparameter. This k nearest neighbor, if we select as 3, now among those 3, say star class is having 2 odds and circle class is having 1 odd, then this new instance will be classified as belonging to star class. Right? Now, if you take k nearest neighbors as 5, now among them, say 4 circle classes are having similar features with new instance and 1 star class is having similar feature with new instance. In that case, it will be classified as belonging to circle class. Okay, so based on the instances, the K parameter, this is important. This term is important. Remember, hyperparameter, or sometimes it is called as meta parameter. These terms you'll come across in machine learning terminology, right? So when you take x1, y1, they are parameters, but the parameters of the data points. But this k is a parameter, and it is not the parameter of the data points. It is the parameter which decides how the machine learning model should consider various neighbors to pick up the class to which a new instance should belong to, right? In that case, we should not get confused between the name parameter. X1 and Y1 are called as features or parameters of the examples or the data points, but K is the parameter which decides how the K nearest neighbor algorithm should work when it is trying to classify the new instance. So K is called as hyperparameter or meta parameter. It is something like metadata. Okay, so meta parameter or hyperparameter tuning is very, very important in machine learning. Only if you tune these hyperparameters effectively, then your machine learning model will perform efficiently. Okay, so the selection of this hyperparameters, say in radial basis function, gamma has to be decided or alpha has to be decided. For every learning algorithm, there are some hyperparameters or meta parameters which have to be fine-tuned manually. Remember, you can't write an algorithm to fine-tune them. You have to fine-tune them manually, iteratively. Check, taking k as 1, k as 2, k as 3, k as 4. Keep checking how your machine learning performs with each of these meta parameters. Say at k equal to 5 means number of nearest neighbors equal to 5. If it is taken, the machine learning model is giving very good performance. So you decide the value of that parameter k to be 5. Okay, like that it is like a trial and error approach. You have to keep trying, you iteratively keep trying which value will suit the hyperparameters the best to obtain good performance from the machine learning model. Okay, so you will come across when we discuss more and more algorithms. I think it is not within the scope of our course, but still when you come across various algorithms in your career, then you will come across all these hyperparameters which you have to focus a lot in order to obtain the best performance from the machine learning models, right? So in today's class, we are going to see the last part of this concept, instance-based learning, that is case-based reasoning. Okay, now I'll just give you a real-life example. Say you are given a problem to solve, or your friend came across a problem, and she or he asked your suggestion how to come out of that problem. In that case, what you will do, you will just memorize anywhere such kind of problem is solved by taking a specific solution, or say they just wanted to find out which university is the best in Karnataka. Now, they asked your suggestion. Now, you will just try to find out the scenarios where your previous friends or relatives joined a particular university. At that time, how they have filtered out various universities and finally selected one best university to join in. That case you will think of, right? Okay, their approach to solve their problem of finding a solution to join the best university is this. This is the approach. They have gone through some portals, they have gone through the brochures of various universities, or they have gone through references of other friends. This is the approach they follow. You try to memorize that. And the same way you suggest to your friend. You can just refer to various portals of the universities, or you can go with or you can just take the opinion of your relatives or friends. Like that, you suggest him some approach, right? What is happening in this case? You are trying to match the present problem with the problem already solved. And what is the approach that have been followed for the solved problem? If it is feasible, you try to apply that same solution to the current problem also, right? You're trying to recollect a case that has been already solved, and that same knowledge you're trying to apply here. That is why it is also called as knowledge based reasoning. You're applying your knowledge in order to do some reasoning, in order to perform some reasoning task, in order to find out some solution to the current problem, right? This is called as case-based reasoning or knowledge-based reasoning. Now let us go into depth and understand it more better. It is actually easier than other kinds of approaches. Instance-based methods such as k-nearest neighbor and locally weighted regression share three key properties. Okay, both are instance-based methods only. In k-nearest neighbor, you try to compare with existing instances, and even locally weighted regression also you try to compare with nearest neighbor properties. Now, in this, what are the three key properties that you have encountered? First, they are lazy learning methods. Lazy learning methods means only the training examples are stored, and until a new instance is given, processing doesn't start. Comparing that new instance with the existing instances and taking some decision to classify it or predict a value is kept pending till the end, until a new instance is given, right? So they are called as lazy learning methods. In that, they differ the decision of how to generalize beyond the training data until a new key query instance is observed. Yeah, this is what I tried to tell. They differ, they postpone, they keep pending the decision of how to generalize beyond the training data until a new instance is given. So it will not keep any generalization ready in order to take the new data instance and immediately predict something about it. Until a new data instance is given, this sits idle. It just stores the training examples. Now, when the data new instance is given, then it will start comparing with the properties of existing instances, and based on some algorithm, it will try to classify or predict that new instance's value. Right? That is why they are called as lazy learning methods. Both k-nearest neighbor and locally weighted regression are lazy learning methods. And second property, they classify new query instances by analyzing similar instances, right? Similarity in the properties, similarity in the attributes, similarity in the features of new instances and existing instances. They classify new query instances by analyzing similar instances while ignoring instances that are very different from the query. Right? Very different from the query means far away neighbors. They are not similar to the query point or the new instance. In that case, we neglect them. We consider only the nearest neighbors. That is another approach. And the third property is they represent instances as real valued points in an n-dimensional Euclidean space. Now, if you take x1, y1, z1 as the properties or attributes of the data point, now all these should be numerical values, right? Only then you will be able to find out the difference between existing instance and new instance with the help of Euclidean distance. If, say, there are attributes like sunny, yes or no, cloudy, yes or no, humidity, high or medium or normal. If you have such labels under the attributes, what will happen? Can you measure the distance between new data point and the existing data point? It is not possible. Why? Because they are in the form of a word, not a numerical value. In that case, k nearest neighbor doesn't match. Okay, so k nearest neighbor takes, or any instance based methods, they normally take numerical values in order numerical values under the attributes in order to find out the nearest neighbors. Okay, so if you have values like 1, 2, 3 or 7, 4, 1 like this, in this case it is easy to calculate the distance, right? 7 minus 1 whole square plus 4 minus 2 whole square plus 1 minus 3 whole square, square root over that will give you the distance between this data point, and this data point, right? That is why the third property is they represent instances as real valued points. All the instances attribute should contain real values, means numerical values in an n-dimensional Euclidean space. N-dimensional means it is dependent on the attributes. Say if you have n attributes, then it is an n-dimensional space. If you have 3 attributes, then it is a 3-dimensional space. Got it now? Now case-based reasoning, hereafter if I use CBR, you just recollect it as case-based reasoning. Now case-based reasoning is a learning paradigm based on the first 2 of these principles but not the third. Now k nearest neighbor, local weighted regression, all these algorithms want numerical values under the attributes. But case-based reasoning will give relaxation for that. You can have even words described as labels under the attributes. You may have words as labels for each of the attribute values, right? So case-based reasoning is a method in which these first 2 principles are followed, means lazy learning and similar instance comparison is followed, but it doesn't put a restriction that the values of the attribute should be only numerical values. It also works with categorical values. So case-based reasoning has been applied to problems such as conceptual design of mechanical devices based on a stored library of previous designs. Say if you have you have to design a pen, or if you have to design a laptop, or if you have to design a vehicle. In that case, for the conceptual design of all these mechanical devices, based on a conceptual design of these mechanical devices can be based or supported by a stored library of previous designs. Previous designs are already existing, right? For this kind of functionality, say when I use this pen and touch the screen, immediately it has to recognize the touch and highlight wherever the pen is used, right? That is a functionality. Now this functionality is tallied with the stored library of previous designs. Say whenever a touch happens, highlighting of that text has to happen. That is a functionality. That functionality might have been already implemented in their organization, and for that design is already available in the stored library. Now that design can be taken out and refined in order to make this pen more better, right? So this conceptual design of mechanical devices or any kind of products can be based on the stored library of previous designs. Previous designs can be referred and used. And it can also be applied to problems such as reasoning about new legal cases based on previous rulings. Now, whenever you study Indian Constitution, when they discuss about some cases, say they are discussing about child marriages. In that case, they refer to some historical cases where some crucial decision have been taken. Say I don't remember her name, but one girl have been married at very early age. Later she continued her education and finished her MBBS and became the first lady doctor in India, right? So such kind of and she has filed a case against child marriages, and the government have taken historical decision that child marriages should be banned. Now, whenever some new cases regarding child marriages have been filed in the court, when they are giving their final judgment, they will try to refer to this historical case where it changed the law, banning of child marriages, right? So I'm giving this judgment based referring to the case of particular doctor who has filed case against child marriages. Means what they're doing, whenever they're discussing something, whenever they're passing a judgment, they are trying to refer to the existing cases, and according to that, judgment will be given. So what is happening here? Reasoning about the new legal cases is being based on the previous rulings, right? Say many other cases. Now, Indian flag can be carried by every common man, if they say. Say somebody have filed a people interest litigation bill against carrying Indian flags by being carried by common man. In that case, they will refer to the person's case who have already filed that every common man in India should have the freedom to carry the Indian flag. Okay, there is one case where some historical law decision has been taken, judgment have been passed. So they'll refer to that particular case. What is happening in all these scenarios? For solving the existing problem, they are referring to previous problems with the same features, and what is the solution there, they're trying to apply to the current problem also, right? This is called as case based reasoning. Solution plan, they will also be used in solution planning and scheduling problems by reusing and combining portions of previous solutions to similar problems. Sometimes old solutions can't be used as it is for the new problems. In such cases, part of the solutions can be taken and they can be combined to form the new solution for the current problem. That can also be done. Now for this, let us take the example of a CADET system. CADET is case-based design tool. Okay, so the CADET system employs case-based reasoning to assist in the conceptual design of simple mechanical devices such as water faucets. Say there is a company called as Jacquard. Now this Jacquard company want to design a new tap and they want to regulate. Say if this is the flow, input flow, this has to be the output flow. If this is the input temperature of the flow, water, then this has to be the output temperature. Now, accordingly, you have to design a tap. Now, for this requirement, there might have already been a design that is well developed and well developed existing in the stored library. Now take that design, take that conceptual design and try to refine it so that it matches your current problem. Okay, that is what is happening. I'll explain you with a figurative example. Now it uses this CADET system uses a library containing approximately 75 previous designs and design fragments to suggest conceptual designs to meet the specifications of new design problems. So in the stored library, it has 75 previous designs. Now among those designs, which design will best suit your current problem of designing the tap? Okay, now among those 75 problems, any one problem's conceptual design can match with this current problem. If not, part of this design and part of another design can be combined together to match your current problem. If not, you can design it newly and store it in the library so that it can be used later by some other people who wanted to create the conceptual design of a new requirement of the tap. Right? In that way, this library can be used or it can be incrementally developed, means adding new designs to it. Right? Each instance stored in memory, say a water pipe, is represented by describing both its structure and its qualitative function. Okay? How the designs are stored? For the water taps, the designs of the water taps are stored both with respect to structure, what is the structural design, and what functionality it is fulfilling. When the tap is open, it has to give the water. If half is open, it has to give half of the flow. If fully it is open, it has to give full flow. If it is turned off, then it should not drip drop by drop. Completely it has to stop the water flow. Like that, some specific design will be maintained for each kind of functionality. Okay, so it is stored in the form of its structural design and the functionality associated with that structural design. Now, new design problems are then presented by specifying the desired function and requesting the corresponding structure. It is quite easy to understand, right, this concept. New design, when some new design problem is given to you, you are asked to design a new kind of tap. In such cases, though the outer design may be more smarter, the underlying structure may be the same, right? When the input flow is like this from the tank, the output flow should be in this way. When the input temperature is this, the output temperature of the water should be this. That design might be already existing. So that existing design you can take and use in your current design of the tap, right? So this problem setting is illustrated in this figure. See this now, how a particular structure of the tab design is stored in the library. Let us see. Now this entire thing is one design having its structure and the functionality associated with this structure. In this example given in CADET system, 75 such designs are stored. Okay, now what is the structure for T-junction pipe? T-junction pipe means the pipe will be in this form. Inlet will be from this side as well as this side, and outlet will be from this end. Okay, so see the inlet, this is the first inlet and this is the second inlet. Now in the first inlet, there is water flow Q1 and temperature T1, and from the second inlet, water flow Q2 and temperature Q2. If these two inlets are allowed into the pipe, into the T-junction pipe, then the outlet will have a flow Q3 and temperature T3. Okay, this is the basic structure of a T-junction pipe. Right? Now, how is the functionality represented? The second part of the library is, the second part of the design in the library is function. This functionality mentions how exactly the combination of this input should result in an output. Now see this, Q1, if it is positive, means say it is increasing in the water flow, and Q2 is also increasing in the water flow, then it should result in Q3. In the same way, if the input is with temperature T1 and temperature T2, then it should result in a temperature T3, right? This is how the functionality is represented in the library. It is quite easy, right? Just if the water flow is Q1 and Q2 from both inlet pipes, the output flow should be Q3. Means you regularize, because Q1 is having certain flow and Q2 is having certain water flow. Q3 should not have double the water flow, right? That has to be regularized and given as a simple water flow. That is Q3. Okay, in the same way, T1 and T2, say T1 is having 50 degrees and T2 is having 50 degrees temperature, both should not result in 100 degrees temperature, right? That is too hot to use. In that case, some regularization mechanism can be applied on the way, and it can be regularized to get the water at 75 degrees temperature, right? This is how the functionality is represented, which is associated with this structure. Now, let us take a problem specification of designing a water faucet. Water faucet means simply a tap, that's all. Okay, so now while designing the water faucet, what should be the structure when this functionality is required? What is the functionality here? Say CT will represent the temperature and CF will represent the flow of the water. Now, when this temperature and flow of the water is given, the water flow should be QC, and when CT and temperature CF is given, sometimes the water flow should be hot. It should be cold sometimes, QC, and it should be hot sometimes, QH. And again, the temperature control also, it should be cold sometimes and it should be hot sometimes. Say when you are applying a geyser, when you are just installing a geyser in the bathroom. Now, based on the input water temperature and the water already in the geyser that is heated, how much water should be output when you turn both the hot water pipe and the cold water pipe. That kind of scenario you can imagine here. Now, QC and QT combination may result in QM, and TC and TH, that is temperature cold and temperature hot, hot temperature and cold temperature, may result in temperature TM. As I said, it should not double the temperature when two types of temperature are coming in. It should regulate. Some algorithm have to be written in order to regulate and get this temperature TM. Okay, this is how the functionality is mentioned. Plus is just increasing the temperature or the flow, and minus is reducing the temperature or the flow. Now, in this case, what should be the structure that have to be adopted? Now, the system refers to the existing library, and for this kind of functionality, which structure has been already used, it will try to retrieve by comparing the similarities in the functionality. Got it? The similarities in the functionalities will be compared, and based on the similarity, the best possible structure will be retrieved and presented to the user. Now, based on that, if it is matching his requirement, he can use as it is. If it is not matching the requirement, at least partial structure design can be taken. If it is not at all matching the requirement, a new design can be built and stored in the library. 3 cases. Complete matching, he can use as it is. Partial matching, he can combine 2-3 designs and make his final design. And if nothing is matching, then a new structure can be developed and put into the library. Now, the top half of the figure shown here describes of a typical stored case called a T-function pipe. What all I explained with the figure, same thing I have given in the slides. Its function is represented in terms of qualitative relationships among the water flow levels and temperatures at its inputs and outputs, Q1, Q2, T1, T2, like that. In the functional description at its right, an arrow with a plus label indicates that the variable at the arrowhead increases with the variable at its tail. So what is the arrowhead? This one. Q3 is the arrowhead and is lying at the arrowhead, and Q1 and Q2 are lying at the arrow tails. Okay. So when we take plus, we indicate that Q3 is increasing with respect to Q1 and Q3 is increasing with respect to Q2. Okay, in the same way, T3 is increasing with respect to T1 and T3 is increasing with respect to T2 when you use plus. But in this case, TM is reducing with respect to QC and TM is increasing with respect to TC. Like that, we can understand the functionality. So plus label indicates that the variable at the arrowhead increases with the variable at its tail. For example, the output water flow Q3 increases with increasing input water flow Q1, right? In that way, it is understood. Now, similarly, a negative label indicates that the variable at the head decreases with the variable at the tail. So if you have like this Q1 minus Q3, then Q3 flow is reduced with respect to Q1. Means Q3 flow reduces when Q1 flow reduces. Okay. Now the bottom half of this figure, in the figure what we have shown, a new design problem described by its decide function. So decide functionality is given. Now what should be the design of the water tap? In this way, if the water flow is in this way and the temperature flow is in this way, then what should be the temperature of the final output water? That is the water coming out from the tap. How is it decided? It is, how is it represented? It is represented in the form of functionality like this. Okay. So if QM has to be obtained, QC and QT will be the input. and Tm has to be obtained. Tc and Th will be the input. Tc is for cold water temperature and hot water. Th is for hot water temperature. So the functionality that is required is represented. Now the user have to decide on the structure of the water tap, in which way it has to be designed. So this particular function describes the required behavior of one type of water faucet. Yes, it is given already. The functionality required is given. Here, QC refers to the flow of cold water into the faucet, QH to the input flow of hot water, and QM to the single mixed flow out of the faucet. If this is the water flow of the cold water and this is the water flow of the hot water, what should be the water flow that is given as output? That is QM, that comes out of the tap. Similarly, if Tc is the temperature of the cold water and Th is the temperature of the hot water, then Tm should be the temperature of the output water from the tap. This refers to the temperature of cold water, hot water, and mixed water respectively. Okay, these terminologies, notations there, just describing. Now the variable Ct denotes the control signal for temperature that is input to the faucet, and Cf denotes the control signal for water flow. Now in this case, this is the control signal for temperature, which controls the temperature, and this is the signal which controls the water flow. Now how are these controls adjusted? If temperature is this much for the water flow and temperature is this much for the water flow, then what should be the output water flow's temperature, so that it doesn't harm the user? In that way, the design has to be made. So given this functional specification, functionality is given in the form of the figure. For the new design problem, now CADET searches its library. Already there is existing library with 75 designs that have successfully solved the problems of similar features. Now CADET searches its library for stored cases whose functional descriptions match the design problem. Existing solutions, functional descriptions which match the current problem, that solutions are taken. If an exact match is found, what will happen? Indicating that some stored case implements exactly the desired functionality. Now there is already one structure developed in the library which is addressing the same kind of functionality. Then this case can be returned as a suggested solution to the design problem. Right. If no exact match occurs, then what will happen? CADET may find cases that match various subgraphs of the desired functional specification. So in this case, say this part of the functionality is matching with the existing structure. So that structure is derived. Now only this part of the functionality is matching with another structure. That structure is also taken. Now this structure and this structure will be joined or made compatible enough in order to address the entire functionality that is given newly. This new functionality can be addressed by combining two existing structures. Okay, if no exact match is found, then combining the structures also can be done. That is what is being told here. Right? If no exact match occurs, then the CADET system may find cases that match various subgraphs of the desired functional specification, bring them, see if they can be combined, and arrive at a final design which will address your current problem. Now, CADET searches for subgraph isomorphisms. You know what is an isomorphism, right? Graphs that are almost similar in their connections. They are called as isomorphic graphs. Say if there is an edge between A and B, there will exist an edge between A and B in the second graph also, right? If such similarities in the connections between, of the functionality are found, then immediately that structure may be useful, this particular functionality. That structure can be derived and see whether it addresses the current problem. If it doesn't address, check for other kind of structure, combine both of them and solve the current problem, right? If at all no match is found, then new design have to be developed, new structure have to be developed. Okay, so the CADET searches for subgraph isomorphisms between the two function graphs so that parts of a case can be found to match parts of the design specification. Parts of a case can be found to match parts of the design specification. Partially the design specification may be met by the existing cases. Now it uses a rewrite rule. Another important feature of this case-based reasoning is it uses a rewrite rule that allows it to rewrite the influence A to B as A to X and X to B. What is this? Say if B is increasing with respect to A, if such structure is not available, you can rewrite the rule as if B is increasing with respect to X and X would increase with respect to A. This can be written in the similar way, that is almost matching this. Did you understand? If B is increasing with respect to A, means if B is increasing when A is increasing, if at all that kind of structure is not available in the library, you can rewrite the rule. How can you rewrite that? In this way. If B is increasing when X increases when A increases. X is said to increase when A increases. This is almost similar to this one, right? In that way, you can rewrite the rules or you can represent the functionalities so that it matches the current existing structures in the library. Okay, this rewrite rule can be interpreted as stating that if B must increase with A, then it is sufficient to find some other quantity. Then it is sufficient to find some other quantity X. If at all you can find a solution with some other quantity X such that B increases with X, then X increases with A, it is same as B increasing with A. I'm repeating again, whenever there is a rule that has to be met, a functionality that has to be met is like B is increasing with A, then if exactly the same type of structure meeting that functionality is not available, what you can do is you can find some other quantity X such that B increases with X and X increases with A. It is indirectly that B increases with A, right? So you're meeting the original functionality with the existing feature by rewriting the rule. This is how case-based reasoning will optimize. If at all the suitable solution is not found, it will try to rewrite the functionalities and try to find out the solution. It will try to optimize its reasoning. It will try to find out the similar solution to the current problem by rewriting the functionalities. Okay, this is how case-based reasoning is optimized. Now, what is the difference between case-based reasoning and instance-based approach? Instances or cases may be represented by rich symbolic descriptions, such as function graphs used in CADIT. Okay, in case-based reasoning, in instance-based reasoning, you don't have that flexibility. But in case-based reasoning, you can use symbolic descriptions as function graphs in order to represent the functionalities of various mechanical devices. Or you can say, you can use rules, well-established rules. If the suspect is having this particular evidence in this case, then this should be the punishment. If this is the range of offense made by a criminal, then this should be the punishment. There are some well-established rules. Based on these rules, in Indian Penal Code, they will try to make a judgment for the current problem. Means they're referring always, they're trying to refer to the existing functional graphs, or they're trying to refer to functional graphs in case of designing mechanical devices, or they're trying to refer to the existing rules in case of judgments. This is how instance-based learning works. Case-based reasoning works. Now, multiple retrieved cases may be combined to form the solution to the new problem, which is knowledge-based reasoning rather than statistical methods. In instance-based learning, normally you used Euclidean distance and Mahalanobis distance, some kind of such distance metrics, or statistical methods, or paid t-tests, or hypothesis test. But in knowledge-based reasoning, you don't have that. You mainly use your knowledge of your existing systems in order to find a solution to the new problems. That is why this is called as knowledge-based reasoning, which is entirely different from statistical methods. And case-based reasoning is search-intensive problem-solving method. It will search first. It will keep on searching for every possible match between the current problem and the existing problem solution. Right? It rigorously searches in the library for the solution. Only if the solution is not available, then a new solution is developed. So case-based reasoning is search-intensive problem-solving method. First it searches, only then it solves. Right? So similarity metric can be modified based on the suitability of the retrieved case. Now, if at all you want to find a similarity between the existing problem solution and the current problem, in that case, similarity metric can be modified so that it is it can be modified based on the suitability of the retrieved case. Now, whether the retrieved case, existing case, is suiting with your current problem, if at all it is not suiting, this can be modified in order to suit the current problem by combining some other solutions. Right? So such modifications can be taken to put the similarity metric in place. Now, in next class, we are going to cover on reinforcement learning. Reinforcement learning is like a child learning to walk. Based on the experience he encounters, he will modify his understanding about taking a step forward. Right? He is reinforced to learn by the surrounding environment. Say if you touch a hot cup, you will feel that sensation immediately. You'll take it back, right? How did you get that sensation? Okay, you touched a hot cup. Because it is very hot, it burnt your fingertips, so you have taken it back. Next time when the cup is giving out fumes, you will not dare to touch it, because you have learned that experience from the surrounding. Okay, when you touch something hot, then it will burn your fingers. So you have learned that experience from the previous case. Okay, so that is called as reinforcement learning. This kind of reinforcement learning, how it is actually implemented with respect to machine learning, we'll see in the next class. Chat box list.
1 second.
No, I'll be there, sir.
No?
I'll be there.
Next, you have event, no? Okay. 2 minutes, madam. I'll talk to them.
Okay, then we'll meet in the next class.
And you recording cancel. Sir.